Welcome to the HPC Best Practices webinar series. The series is brought to you by the IDEAS Productivity Project, funded by the Exascale Computing Project. The series is a collaboration involving the US Department of Energy and Computing Facilities at the Argonne, Oak Ridge, and Lawrence Berkeley labs. I'm Wesley Marcus from Lawrence Berkeley. Ashley from Oak Ridge and I will be the hosts for today's webinar, What's New in Spack? And the webinar will be presented by Todd Gambley. Todd is with the Lawrence Livermore National Lab. Todd is a computer scientist in the Advanced Technology Office there at Livermore, and his research focuses on scalable tools for measuring, analyzing, and visualizing parallel performance data. In addition to his research, he leads the reproducibility analysis monitoring and performance team there at Livermore, and he's also the lead for the software packaging technologies project in the Exascale Computing Project. He's the creator of Spack, we have sold more than 250 tickets for today's webinar. We'll be all attendees have been muted, so we'll be receiving questions through the Zoom chat and also the Google Doc that you can see the address and the screen. So the webinar will have a break so the speaker can respond to the questions that come in. So with that, I'll stop sharing here, Todd, and you take over, please.
Okay. Right. Get that set up. Okay, can you see this?
Yes.
Okay, great. Thanks, Osni. So this is a different kind of talk than I usually give on Spack. I'm used to giving tutorial talks, and this is about new features and the roadmap ahead. There's going to be a brief recap of what Spack is and what Spack does, but we're mostly going to talk about new developments and things that you might be interested in for the community. So before I get started, I wanted to mention there is, for people who like to talk, virtual Spack tutorial July 28th to 29th. You can register at this link down here. It's just like the ones that we give at SC and ISC, but it's for everyone. And so if people are interested in this, please go to Spack tutorial on aws.splashthat.com and sign up. We're teaming up with Amazon Web Services to offer this. They're providing the resources that we're going to run on, and I think it'll be good. We've given one online tutorial before, and it went pretty well, and I think we're going to be able to do a good one for even more people now. All right, so just as a review, Spack's a package manager for HPC. It lets you install things on your system the way that you want to. So if you wanted to install, say, a tool called MPI leaks with Spack, you could say Spack install MPI leaks. That's unconstrained. It says, hey, just get this thing on my system. Do it whatever way you can, and I'll accept the defaults. I don't care about any of the other details. Spack is different from other package managers because you can do things like specify specific versions. You can say, I want version 3.3 of that tool, or I want it built with a particular compiler, or a particular compiler at a particular version. You can say that you want particular options for the different packages, and you can inject things like compiler flags into the build, or set the build target to a specific architecture instead of just the default for x86. And this whole syntax is recursive. You can go through, you can install for, you can specify all of these different constraints for your dependencies as well as for the root package. So you have a lot of control, which is something that HPC people tend to like. The idea is that you just specify what you need, and Spack tries to take care of the rest and spares you the details of configuring a large stack of software. Spack packages themselves are templates, and so if you wrap your software up in a package so that you can distribute it to other people in Spack, it looks kind of like this. Every package is a Python class. It has a little metadata up at the top that tells you where to download it, where to get the tarball, what versions are available, checksums for them so that it knows that it's downloaded the right version, and then things like options that are available on the package and so on. This says that this is the cryptkey package. It's a small deterministic transport app from Livermore. It depends on MPI and CMake. It can be built with MPI optionally. It can be built with OpenMP. And these are the instructions down here for how to build it. So this is saying these are the CMake arguments. This is how you enable OpenMP and MPI, if depending on how the user asked for the software. And then this is how you install. And essentially in Spack, the packages are just templates that tell you how to go from a spec, which is what the user types on the command line. That's this spec here. to a prefix, which is where you install the package. So it's just a Python script that says, hey, build this thing this way. And all you're doing is you're translating this spec that the user specified into an actual installation of the software. So it's easy to make packages, and this is what a typical package looks like. They can get quite a bit more complicated than this, but this is the gist. All the stuff about how it can be built is up here, and the instructions are down here. Spack handles combinatorial complexity. So if you build a template like this, you may want to build lots of different versions of your package. And essentially in Spack, every unique graph, every configuration of the package is a unique configuration, which maps to a unique installation. So if your software looks like this, and this is MPI leaks, it depends on call path and MPI. Call path depends on the dynance library, which depends on libdwarf, which depends on libelf, and so on. Every different configuration of any of these packages means that MPI leaks will have a different installation. It's a Merkle DAG. Basically, we hash these things, and each one of these packages that we install gets a unique directory where we install those things. We manage the dependencies by embedding RPaths into binaries. So if you were to run the MPI leaks tool out of here, it would know where the libraries for all these other things are, because we embedded that in the executable and in the libraries. And that basically enables you to have lots and lots of different versions that can coexist with each other, because each one knows which specific directory in here its dependencies correspond to. We try to avoid things like LD library path in Spack because they're kind of unwanted global variables. You set them in your environment and they sort of apply to everything. And often if you're dealing with different versions of dependencies, that's not what you want. You might want to run one application with one version of MPI, another application with another, or so on for different dependency versions. So this is how we manage combinatorial installs. Sort of the core of Spack, and something that I'll talk about later, is called the concretizer. This is how we do dependency resolution. It's how we go from this syntax here, MPI leaks, depends on call path at version 1.0 with the debug option, and depends on libelf at 0.8.11, to a concrete installation. And so the user gives you this, and they say Spack install MPI leaks, blah, blah. And what we do is we turn that into a abstract graph. And so this is MPI leaks, and you can see that the constraints from the spec have been put on the DAG, and we fleshed it out to include all the dependencies that we know about. As we do that, we then stick it in the concretizer, and that gives us a fully specced out graph. And so what you're seeing here is every compiler, every version, every option has been set in this DAG. And this is basically what is passed to the template to install. So by the time you get to your build instructions, you already know what you're supposed to build, and you don't have to do a lot of things like poking around on the system and seeing if some package is installed in some location. You already know, Spack told you. And so all you have to do is say, okay, if the configuration looks like this, build this. If the configuration looks like this, build this. Set the architecture to whatever it says, and so on. And so that really simplifies the process of writing build scripts. For every package, we store this information on the disk in a YAML file. We have a database of these things that tells us all the installations that have happened, all their hashes, all their metadata. So you can query for installs and manage lots of different installs of the same packages together on the same machine. So it's good for benchmarking, it's good for large facility deployments, it's good for development because you can build lots of different versions of things. And we're trying to enable the thing to be as flexible as possible to give HPC users the control that they tend to want. You can use Spack spec to see the results of concretization. So this is what Spack will spit out to show you, how it actually built the MPI leaks tool. You can see that the real tool is a bit more complicated than what I showed in the example. But here are all the packages. This is MPI leaks at version 1.0. It's built with this compiler and it has this architecture. This is Boost. It has a million different options. This is what they're set to, and it's built with this compiler and this architecture as well, and so on. Spack, we started the project in 2013, and it's gotten to be pretty popular since then. We started with, when we first went public, maybe 170 software packages, mostly written by folks at Livermore. We're up to 4,300 software packages in the mainline with almost 3,000 monthly users of our documentation site and over 600 contributors. And so we've really managed to grow the project where we have worldwide participation, and most of the packages are contributed by people external to Livermore. It's a big collaboration of a lot of different sites. This is the growth of our users on the documentation site over time. So you can see, the monthly active users, I guess as recently as 2018, was down around 1,000, but we've grown up to 2,000 in the middle of 2019, and then now we're up close to 3,000 monthly active users on the doc site now, which is pretty exciting. It's also pretty daunting because of how much activity there is on the site. And so Spack is used on a number of the top HPC systems. So Fugaku, it came to Riken, it's #1 now, is deployed using Spack. The user stack on Fugaku was built there. We've had a collaboration with them since they started setting up the machine. They liked the tool because it was easy to get packages running on ARM and to add patches and things to existing open source software that they wanted built on the Fugaku machine. Spack's been used on Summit at Oak Ridge. The Oak Ridge folks build about 1,300 packages on that system with Spack. They can rebuild it overnight or in a few hours. And Spack has really sped up the deployment there. Livermore uses it on Sierra, and then machines like SuperMUC NG in Germany use Spack as well. So we have a lot of the big machines, in addition to the sort of more small commodity HPC systems. This is what 1 month of Spack development looks like on the project. So this is June 2020 to July 2020. This was a couple days ago. You can see, we have a lot of contributors putting things into the project. So it's not just a few people contributing to Spack. It's a lot of different people. There's obviously some core developers who contribute more than others. But we merged 333 pull requests from all sorts of different people every month, which is pretty cool. And we're grateful to members of the community who just volunteer to help maintain the project. It's not just our core developers, but other folks who have volunteered to just take part in the project, review pull requests, and make sure that they get merged. The contributions are growing. You can see that they're pretty diverse. This is showing the history of the project since about 2013 when we started up until now. This is the core up here. And so this is the main Spack tool. And you can see that about half of it was written by folks at Livermore. And that's still true today, but we've gotten a lot of different contributions from other organizations. And then down here in the packages, it's way more diverse. So Livermore is this top chunk, but we're probably less than 10% of the total contributions to the package stack in Spack. And that's the recipes themselves. So we mostly maintain the core tool these days. All right. So that's the sort of a review of the Spack community and the core features. I wanted to talk a little bit about what we've been doing to change kind of the workflow to manage the project over time. So one thing that we've done is we've developed a release workflow starting from about, I guess, 2 supercomputings ago from 2018. We started making these project boards on GitHub. And they look like this, where there's to do, there's in progress, there's review in progress, and so on up until done. And essentially, if we have major features or things that need to get implemented for particular releases, we put them in a project board per release. So we're doing major releases, which are things like 0.13, 0.14, and so on. And we put big features into those, and we also have point releases, but each one gets a board. And it makes it easy to schedule work. We're trying to crank out releases more regularly so that you'll have tarballs of Spack that you can rely on. And if things don't get done for a particular release, we'll just move them to the next one. And so we're really trying to do this on a regular sort of clock as opposed to when things are ready, which tended to slow down our release process. So we're shooting for quarterly releases. I think we're hitting about 3 or 4 releases per year. And I'm going to talk about some of the more recent ones in here. 3 or 4 major releases. We do bug fix releases as well. And so that's what this looks like. This is what bug fix releases look like. We've developed this branching strategy where I think most people still use Spack on the develop branch. It moves along over time. But at different points in time, we branch off a major release from the develop branch and we'll tag it. So this would be 0.13 here. And we've started backporting bug fixes to these stable releases so that they get more stable over time. Essentially, we'll break off a 0.13 release. That includes a certain set of packages at a certain set of versions, and that's what we freeze with the releases. And then we backport bug fixes to the core tool on top of that. And so over time, if you check out 0.13, you can upgrade to 0.13.1 without any disturbance to your software stack, no changes in the packages or anything, just fixes in the core tool. And then eventually we'll bring out 0.14 and so on. We're up to 0.15 now, and we keep backporting bug fixes to things. We just put out 0.15.1 and we're working on a 0.14.3 release to include some of the fixes that were there. So our expectation is that people can rely on these releases over time. If you want to maintain something like a stable facility deployment, you could pick a Spack release and just keep pulling on the release branch to get these bug fixes without disturbing the stack. That's the idea. And if you want to stay on the bleeding edge, there's always develop. We do CI on develop, and I'll talk a little bit about that later. All right. So Spack 013 was released in November at Supercomputing 2019. It had some pretty big improvements to the stack. So Spack Stacks was the main one. This is some extra deployment logic for facilities, as well as this specific microarchitecture feature in chaining. I won't talk about chaining, but the other two are the big ones I wanted to talk about. So the main thing that you'll notice if you check out a Spack version that's more recent than 013 is that it does not build for just x86 64 anymore, or just PowerPC 64 LE. It builds for a specific target. And what that means is, if you've ever tried to figure out what your processor is on your machine, this is what it looks like. So you get a lot of information from proc CPU info or from syscontrol on Macs, but it's not really intuitive. You get something that looks like this. And so this says Intel Xeon CPU ES2695. There are a bunch of features down here, but it doesn't really say the name that you're used to. And so we don't know what that is. We know that these are the features that we kind of care about, but they can be a little opaque as well. And most people would call this Broadwell, and they would know what that means. And so one of the things that we've done in Spack is we've built the packages for specific architectures now. So we have this support where if you do Spack arch -- known targets, you can see all the different targets that Spack knows about. That includes generic ones, so that you could build for a generic target. But we will also try to build packages for the most recent architecture available for your system. So if you're on a Skylake machine and Spack knows how to detect that, we will say this is a Skylake machine, and we'll build Skylake binaries. The one exception to that is if you have an old compiler, we also know what compilers can generate code for different targets. And so if you have a compiler like GCC4 that can't generate code for recent architectures, then we'll downgrade the target so that we know what it was built for and what it's compatible with. And so we can do things internally like compare Skylake to Broadwell. We know that Broadwell binaries are compatible with Skylake because Skylake is more recent, and that Skylake binaries are not compatible with Broadwell, and so on. This has also enabled us to simplify packages, and things like OpenBLAS and some of the packages that really do care about architectural features used to have to jump through hoops to figure out what was available on the current machine. And so they would duplicate this kind of logic. Now they can just ask. They can say, if AVX512 is in spec.target, so that just means if my architecture supports AVX512, then just add the AVX512 option to the config line. So it's much easier to write packages like this, like OpenBLAS and FFTW, where you care about these vector instructions. The other thing that we can do is you can specify the target on the command line. So you can say Spack install, say LDAN or PETSI, and target a specific microarchitecture. So if you're on a Skylake machine and you don't want to build for Skylake, you could build for Broadwell. You could build for an older architecture that doesn't have all the instructions if you want to be more portable. And people do that for things like hybrid clusters where they have different types of processors. But by default, we will build a binary and we'll say, hey, this binary is good for Skylake, so that you know where you can use it. We spun this library out because we really like to get vendor participation to track all these different CPUs. And so it's called ArchSpec. You can go to github.com/ArchSpec. This is actually a collaboration with Kenneth Host from EasyBuild. And we would really like to have vendors contribute specs of their latest chips so that we can detect them all and query the features correctly. And so we've actually gotten 2 new contributions just recently to ArchSpec for Graviton and Graviton 2, which are the cloud ARM chips. And so I think it's working so far, at least a little bit. But we'd like more. So if you know vendors who are putting out chips and you have a connection there, recommend this to them and tell them to contribute to ArchSpec so that we can have a library to detect this stuff and get common names for these architectures so that we can easily distribute binaries for them. So that's something that came out of 013. All right. So the other thing that you may remember is in Spack since 012, we've had environments. And environments are a lot like virtual environments in other package managers like Conda or Python's virtualenv tool, where essentially you can group a set of installations together and load them up so that they're all in your environment at one time. What we've added to this is we've tried to combine the features of other package managers that have manifests and lock files, where if you've used cargo or something like that, there's a cargo.toml that says these are the things that you need to install, and it'll spit out a file called cargo.lock that says this is what I built exactly. And so in Spack, we have this file called spack.yaml that can include some configuration for how you want things built. You can include external files, or you can just write the configuration, like what your concretization preferences are and things up here. And then a list of specs. And these are just the same kind of specs that you would write on the command line in Spack. So HDF5, libalf, OpenMPI. And you can put options on these. So if you want OpenMPI built with a particular fabric, you could put that option on there. If you want HDF5 with the parallel library, you could do HDF5 plus parallel, and so on. If you just say, if you activate this environment and say Spack install, Spack will go and install all of these different specs, and it'll spit out what we're calling a spack.lock file that has specifically what it built. And so essentially this is an abstract spec for a bunch of packages that you want to use together. And this is a concrete spec for a bunch of packages that you want to use together. So if you wanted to reproduce this stack, you could take the lock file and rebuild from it on the same machine. It's tied to the machine. If you wanted to reproduce it, functionally, but not exactly like it was built on another platform, you can take this YAML file and hand it to someone and say, here, install this. And so the idea is that you could take the same spack.yaml and build it on, say, an Intel machine or a PowerPC machine, and have different spack.lock files for those two configurations. And so it's sort of a requirements and a what actually happened model with a file format associated with it. Now, so this is simple for a single prefix where you want everything in one environment, but it's not something that's scalable to a facility deployment, at least not until 0.13. So in 0.13, what we did was we added this thing called Spack stacks, where you can have combinatorial elements in an environment. And so what this means is you can define something like this. You can say, here's some definitions. There's a compiler list here. This is GCC 5.4, Clang 3.8, Intel 18. You can have some MPIs, and you can have a bunch of different packages in here. And in your spec list, instead of just a list of specs, you can have a matrix. And what this is saying is just take the cross product of these three lists, or take the Cartesian product of these three lists. And so it says build Nalu, HDF5, Hyper, Trilinos, and PETSI with all combinations of these compilers and these MPIs. So it'll build Nalu for GCC and MVAPage. It'll build Nalu for GCC and MVAPage 2.3. It'll build Nalu for Clang and MVAPage, and so on. And so it's easy to specify very large combinatorial matrices of packages for a facility. And we spit out the same kind of lock file for this, where once you're done installing this, there's a lock file available, and you could reproduce the installation from it. You can have, for each of these stacks, its own module configuration. And so down here, this is LMOD configuration here. You can set how the packages are named in the module hierarchy and so on, what's included in the hierarchy. And so that's good for facilities. They can have some module configuration associated with their packages. And the hope is that we can make what used to be some fairly complicated scripts into a simple configuration file for facility installations. There's tweaking that needs to be done when you do these installs at facilities, but that's the goal. The typical Spack stack looks a bit more complicated than this, at least right now. All right. So Spack 0.14 was released earlier this year, and this added a bunch of other new features that build on these environments. And so what we're really focusing on is how can we flesh out the environments so that they're useful for lots of different workflows. So there's GitLab pipeline generation, where we have CI integrated with the environments. You can generate a container recipe from an environment now, and we added this distributed and parallel build feature. So I'm going to talk a little bit about those. So the parallel builds are done a little differently than you might expect. It doesn't require resource manager integration or anything. Essentially, we made it so that Spack works correctly when run concurrently. And so we implemented a distributed locking algorithm. It knows about F-control locks on your file system. If you just run two Spacks side by side and tell them to install the same thing, they'll coordinate on which packages to build from the bottom up. And so if you build Trilinos and you want to help out your existing build because a few more cores came available on your login node or on another login node, you could just run another instance of Spack, and it would see what locks were held by the other Spack instance, and it'll build the ones that aren't currently being built. We've implemented this so that it knows where all the dependencies are, and you could run 4 of them or 10 of them together for a parallel build. So you don't need any particular resource manager integration. Spack doesn't have to know how to talk to Slurm. You can just say srun-n8-n32 Spack install, with some level of parallelism for the Spack install. And this will basically spawn a whole bunch of Spack jobs out on the nodes of your cluster that work together. The other sort of benefit of this is for multi-user installations. If two users are running together, they will coordinate correctly and they won't step on each other. So that's an improvement that happened in 0.14. So in addition to that, we've been expanding environments. And so one of the features that we added for 0.14 was the ability to take a Spack environment like this, where you have a list of specs like growmax plus MPI and mpitch, and generate from that a multi-stage Docker recipe. And so what that means is you can pretty much take any environment. You don't have to specify all this container stuff that I'm showing here. You can take any environment and you can say Spack containerize with the environment activated. And what we'll do is we will generate a recipe where we make one image that has the compilers and such in it, and we install all of that. We build the artifact, and then another, and it'll make another image that just has the things that you want to run. So the final version of this image will strip out all the compilers, all the build dependencies, and all the things that make the image really big. And you'll just end up with growmax and mpitch installed, along with all of their dependencies in the final image. We strip the binaries, and so we can make some pretty small images out of this. And you can see here in the Docker file, it's a little tiny, but there's a builder image here. We're using this multi-stage syntax, and then there's the actual final artifact here that copies in all the things that were built from the build image. And essentially, the build just uses Spack inside. And right now, we base this on Spack images on Docker Hub, but we have some stuff in flight where we will allow you to specify different base images for this. So you could basically build your Spack environment with whatever base image. If your facility wants a particular one, or if you have a particular OS you like, you could install Spack stuff on top of that. That's the goal. But this exists, it's in 0.14, and it'll generate you a recipe like this. We can generate Singularity recipes too. They don't do the multi-stage stuff because at the time we wrote this, Singularity didn't support multi-stage builds. I forget if they do now, but hopefully this is still pretty useful to people. And you can run your Docker images in Singularity anyway, so you can still use Docker to build and Singularity to run if you want the small images. So on top of that, the other thing that we've added to environments that came out in 0.14 is we've been working with Kitware. They have done a lot of implementation of CI automation. And so if you think of these YAML files that we have in Spack, where you have some definitions and a matrix of packages, or maybe you just have a package list, you might want to build that in CI. What you can do is you can specify a GitLab CI section in your YAML file, and you can specify these things called mappings here, where what this is, all this is really saying is, these definitions in this matrix will result in a list of things to build. It's going to come out with a list of concrete specs, and they're going to have different attributes on them. Like they might say, this one needs to be built for Ubuntu, and this one needs to be built for CentOS, and this one needs to be built for Skylake, and this one needs to be built for Broadwell. You can have matching syntax down here, where essentially you have mappings, like this says Spack Cloud Ubuntu. This matches all the specs that are for Ubuntu 18, and it says run these on a GitLab runner in Kubernetes that has this builder associated, that uses this image. And this is an Ubuntu image. And then for CentOS, what you're saying is, I want to build that, I want to build everything that should be built for CentOS with a CentOS image. And so it lets you set up a build farm essentially on any GitLab instance. And what we generate is this DAG of jobs in GitLab from your environment. So this is another way to build in parallel. You can fire up a GitLab instance, you could use another GitLab instance. We will farm the jobs out to all of your runners in the GitLab instance using Spack CI. And we're leveraging some newer features in GitLab to do this. We had older versions that used multiple repos, but there's been a recent feature in GitLab that lets you essentially generate the YAML to describe your build on the fly. And so you can make a repo with just this YAML file in it. You can run Spack CI in it, and then we will generate a child pipeline from the job that ran Spack CI with all of this stuff in it. So it's pretty automatic. You can send progress reports to CDash. You can see an example of that at cdash.spack.io. But this stuff is working, and this is in 0.14. This is documented in the pipeline section of the Spack docs if you want to take a look at it. One way that we made use of this workflow is we took the image that we used for our Spack tutorial and we built it in Spack CI. And so we have a repo on GitHub over here that we have hooked up GitLab CI to. GitLab has this ability to do CI for a GitHub project. This generates a pipeline over in GitLab Once the pipeline passes in GitLab, we report status back onto the GitHub job. And once that's done and merged into the master branch on this repository, Docker Hub picks it up and just builds a container with the binaries that we generated in this build process. So essentially, this pipeline can populate a mirror of binary packages where you have all of the artifacts that you need available. And then when you go to build on Docker Hub, there's a time limit on these builds, but it doesn't matter because you're just installing binaries at this point from the pipeline that generated them over here. And once that's done, you can go and run the container with Docker. And this is how we build the container that we use in our Spack tutorial with all the binaries in it. One of the goals that we have under ECP is to get this kind of CI going at different facilities at different laboratories. And so this is not done yet. These sites are not running pipelines yet, but our hope is that on major supercomputer centers or on major machines at the different labs, we could have this GitLab CI stuff running, and then we could upload binaries to a public mirror. And then users could come along and download the binaries and they wouldn't have to build. That's what we're working towards. We're not there yet, but you can see how all these pieces fit together to do this. The specific target stuff basically means that we can use the binary, we know where we can use the binaries that we generate in Spack. And then with this public mirror that we're setting up, we would be able to download them for Spack users. It's not done yet again, but this is something that we're working towards under ECP. All right. So Spack 0.15 was released 2 weeks ago, so this is getting us up to the present. There were a lot of different features in this one, but I think the biggest one is this external find command, where essentially now packages can specify how they could be found on the system. I'll talk a little bit about that. There's a source code mirror for Spack packages. I'll talk about that. And then we've actually started using some of our CI to test the builds in Spack, and we really hope to expand that. There's better Cray support. We're working pretty closely with Cray on the El Capitan and Frontier contracts to support Spack and make sure that it works in that environment. So there's a lot of detection improvements and things to make Spack work across different Cray systems. And we're working on features that would enable us to better know what's in the Cray programming environment and how best to use it when we concretize Spack packages. And there's a few other features here I'm not going to get into. All right, so Spack external find is new. It used to be that you could just specify your build instructions in your Spack package where you said, here's how I install this thing. I'm given a spec. Now I have to build it and install it on my machine. We've also had this feature in Spack for a long time called externals, where you can specify, here, OpenMPI at 1.14 is installed in this directory, and you could tell Spack about your software that's already on your system, and you could build against it. It's a bit of a pain to set that file up, and so what we've done is we've made it so that packages can do something a lot like what we do for detecting compilers already. Whereas the CMake package, for example, now says, hey, my executables look like this. There's an executable called CMake. And if you find something like that in my path, go and run this function to query it for what exactly kind of CMake install it is. And so basically what this does is it builds a spec. It says, hey, CMake at 3.14 is installed in this prefix that I found while I was going out and querying the user's path. And it'll generate the configuration that you need for that. And so you can see here that you've got packages, CMake paths. And now it says CMake at 3.15.1 is installed in user local. So what that does is it takes the burden off the user to specify all this stuff, and it sort of standardizes the way that we query external packages, and the user doesn't have to know how. They don't have to know quite as much about how to query a package for a version. It can just be in the packages. We've only implemented this for a few packages so far, like CMake, but as always happens when we introduce features like this, we have a bunch of rather OCD people on the Spack project who just love to take features like this and expand them to all the packages. So you should be seeing lots of support emerging for different sorts of build dependencies, at least in Spack. I think we can get this working for things like MPI as well, but it's a little tricky with libraries. And so, this right now, what we do is we find executables in your path, we query them. And so for MPI, that'll work. We'll be able to do things like MPI cc-show me, to query information about libraries. That can give us versions, it can give us libraries and things for the MPI implementation. But for libraries where we don't have a wrapper like this, it's a bit harder to query. And so I don't expect this to work for all different libraries on your system, at least not right away. But what we'd like to be able to support is somehow inspecting those in the future to figure out their properties, but we haven't worked that out yet. So think of this as a feature for detecting all of the sort of troublesome build dependencies that you don't usually want to build in Spack. You can find them from your environment and then go and focus on building the thing that you want to build. The other thing in 0.15 that we've added is we've introduced a source code mirror. So if you've been using Spack for a while, you may have noticed that the packages tend to download from authoritative sources. Some of them have mirrors in them, like the GNU ones, but big outages would cause Spack to not work. So if SourceForge goes down, if the GNU mirror goes down, you would just get an error fetching and you couldn't fetch your tarball. But now we've deployed a mirror of our own, where basically we're putting all the different sources and patches and other resources that you need to build on the web in our own S3 bucket. And so this is now the first place Spack will search for packages, and it'll download the binary from here if it can, and if not, then it'll go and find it in an authoritative source. And our goal is to keep this populated with basically everything in Spack, so that if other things go down, we're still in business, you can still build, and you can rely on Spack even on weekends where GNU is moving their servers from one closet to another, as happened, I think, earlier last year. The other thing that we've started doing in 0.15 that you might not notice is we've started using ECP's E4S software stack to test Spack. And so what I mean by that is Spack contributions are coming in on GitHub all the time. We're using the CI features that I pointed out earlier to test E4S with a YAML configuration just for E4S. And so E4S itself is like 50 or 60 different packages, and with dependencies, it's like 250 of them that ECP cares about. It's coming out of the US Exascale project's software technology stack. And every time that someone contributes something to Spack, we are triggering Spack CI and building a pipeline to test all these builds. And so if they've changed from one commit to the next, we will rebuild them and make sure that they still continue to build, at least in cloud environments. And so right now we're doing this in a Kubernetes cluster on AWS for about 250 packages where we're building on CentOS 6, CentOS 7, and Ubuntu. And we're hoping to expand the number of OSs, compilers, and architectures that we provide there. Livermore's also, we're working on getting a cluster set up in the open where we could basically run on the architectures we care about. So we would have some NVIDIA nodes, some ARM nodes, some Power nodes, and maybe some AMD and AMD GPU nodes that we could do builds on. We haven't gotten that set up yet, but this is sort of the direction we're going, where we'd like to just expand this CI and start testing on more and more platforms and get get Spack vetted. And so right now we do this on PRs, where we run a pipeline, and the status, you can see the status update on a lot of different Spack PRs right now. At the moment, because of a limitation in GitLab, we're only doing this on PRs that originate in the Spack repo, but this will be happening on all PRs soon. And then we're also doing this kind of testing on our release branches. And so for 0.15, we ran the whole E4S stack. It builds in our cloud environments, and we're able to vet releases that way. Eventually, this will be used to populate a public binary cache, like I was saying, where we basically have all the E4S binaries available in Spack. And so if you clone Spack and try to install something that's in the ECP stack, or as we expand this, other stacks, you'll be able to install it from binaries. And so you can learn more about E4S at e4s.io. That's down here. And there's a lot of details there about what's in the stack and about the work that goes into maintaining these particular Spack packages. All right. So for the last part of the talk, I want to talk about the concretizer, which is kind of at the core of Spack. And like I said, this is the thing that takes the abstract spec that you specify on the command line or in one of these YAML files, and that turns it into the concrete spec that we actually build in Spack. And in Spack, this is pretty complicated. We have a lot of different places where we can pull build information from. So we get it not just from the command line, not just from environments, but from local configuration, from Spack defaults, and from the package repositories themselves. There's information in all of these places that affect the defaults and what the constraints are on how we can build a particular package. It turns out this is an NP hard problem, and the current implementation in Spack is actually using a greedy algorithm where we make some decisions. We make some decisions too early. We will say, this node is at this version without looking for whether there's a conflict down the road, and so this can cause conflicts to be reported where they really shouldn't be in Spack, and we don't do enough backtracking to solve all the different places that we need. To add to that, the code's gotten pretty complicated because we're pulling from all these different places, and so we needed a new version of the concretizer. So I'm going to talk about the prototypes that we used for that. If you think about what is managed by most dependency managers, it is something like the name of the package and the version. And so that's, and maybe some dependency constraints like this, where this name and version depend on, so foo depends on bar at greater than or equal to 2.0, and baz depends on, and baz greater than 3.0. But the package model is pretty simple. It's just a name and a version, maybe some features for systems like cargo, but it's not a lot of detail. In Spack, we're solving for a lot more stuff. So this is a typical package manager. These are all the types of things that we put into a Spack solve. And so it's all those things I showed on the first slide. It's the version, the architecture, it's the compiler, all the different build options and compile flags, and also all of that for all the dependencies. And so we have a lot more stuff to consider when we do a solve on this stuff, which is why we wrote a custom concretizer in the first place. Stat solvers are what people typically use for this, but they are pretty low level. So if you look at what other systems use for solving, Conda uses picostat with a bunch of booleans, with a bunch of custom logic on top of it to do arithmetic and to do optimization. There's a thing called libsolve that can do this sort of package version model of packages and solve cases like that for other package managers. It's used in things like the SUSE package manager, and I think by Yum as well. But it's not extendable to all the things that we want to solve for in Spack. And so, we've been looking at ways that we could implement something like this, but more sophisticated. So the two things that we settled on that we could potentially implement the Spack concretizer in were SMT solvers, which is called satisfiability modular theories. These are logic solvers, but they also have things like you can do arithmetic constraints, you can do optimization. You can spit out proofs of why things are unsatisfiable. There's some pretty cool features in tools like Z3. And then ASP is called answer set programming, not active server pages. This is another type of solver that uses something that looks like Prolog as the input. It supports a lot of the same features as Z3. And the main ones that we need are, we like the first order logic, and we want to be able to do optimization on the specs. So we've been looking at these. We have a prototype in ASP. We're using Klingo, which is the Potasco grounder and solver package. It's a combination of something called Gringo, which is the grounder, and Clasp, which is an ASP solver. And essentially, this simplifies our algorithm quite a bit. Instead of having to write this rather Baroque algorithm for doing all of the things that we do in Spack, we can write a declarative program that just has a list of facts generated from our package repository. And so for a typical spec in Spack, 6,000 to 9,000 facts is typical. It looks kind of like this over here, where you can see like this is for UCX. We have version declared UCX 161. That's our favorite one. Version declared UCX 160. That's our second favorite one, and so on. This is information about variants. There's information about dependencies in here. There's lots of different facts that we're solving on in these Spack packages. And then in addition to that, we have a small logic program that I guess is now about 300 lines that has the core logic over these facts that we use to guarantee valid concrete specs. And so that's what we do. And the algorithm essentially underneath just searches for a configuration that satisfies all of these things. It's a lot more sophisticated than that, and these things can go pretty fast. But that's basically what we're doing. We say what the spec should look like, we say what the facts are, and then we go and we solve that with these ASP solvers. Typically, the solve itself takes a fraction of a second right now. The grounding takes a while because essentially it has to convert a bunch of first order logic clauses to clauses for each of these propositional facts in the program spec. And so that can take a while, but at least the solving is pretty fast. It can fall off a cliff sometimes, and so we have to be careful about how we construct it. This is kind of what's taking the concretizer a while to get implemented. There are places where certain aspects of a spec can be slow. When I tried to optimize versions and targets and compilers at the same time, I ran into certain situations where if I didn't set some heuristics on the solver, it would fall off a cliff and take a long time. The nice thing about this is it makes it very easy to put the logic in one place. Essentially in ASP, what you do is you define the space of packages, and so, or the space of possible solutions. And so what this is saying in sort of cryptic Prolog language is that if something is a node in the Spack DAG, that implies that there's exactly one lower bound one, upper bound one version on that node out of all the possible versions. So basically, this is saying the space of things. Every time you have a node that you discover, there's a certain number of possible versions for that node, and you have to pick one version from all those possible versions. We say things like, if a version is declared, but it's conflicted, if there's a conflict, then that's not possible, that's not a valid solution. And then we put in these sort of minimization pragmas here that say, we weight the versions according to some preferences, and then we just minimize that weight over the whole DAG. I'll talk about why we minimize it later. But this is a pretty simple spec that says an awful lot in not a lot of words. So it makes our algorithm more maintainable. Other logic has become pretty simple as well. So one of the problems that we had in the previous version of the concretizer is that there was a little bit of a chicken and egg problem between picking a target and picking the right compiler to use for a build. So if the user if the user picks a compiler, then you can pick sort of the best target that compiler supports with respect to what you're building on. If the user picks a target, you could pick the compiler that supports that target or the most recent one. But if they don't pick either, you kind of have to optimize both of those at the same time. And so all we do now is, instead of having some complicated logic where, one side of the solver, one side of the concretizer says, if the compiler is set, then, pick a target. If not, then wait for the compiler to be set, and so on. Now we just say, don't make nodes where the compiler for the node doesn't support the target. That's all we have to tell the thing, and then it's smart enough not to pick configurations that look like that. So this has been pretty cool to specify things in ASP. Dependency logic is more concise than it used to be. This is a lot less code than what we had. I won't get into all the details here, but we can do things like specify virtual dependency logic pretty easily. We can say, if there's a node and it's supposed to be an MPI, then you can pick one of the MPI implementations that's available, and that's what should go on the node. There are lots of really simple things that we can say, and then throw that to the solver and let it deal with all the complicated logic that stems from that. Not everything was simple. The learning curve for ASP and for solvers in general is pretty high. If you haven't been exposed to this domain before, it can take a while to get in the right mindset for doing a solve on these large combinatorial spaces. And the thought per line of concretizer code is a lot higher than it used to be because there's a lot less code. The examples look simple when you tell them to someone, but coming up with them is a lot harder. So that can be tedious. Structuring the optimization criteria can be a challenge. So for example, picking whether to maximize or minimize something is interesting. Things can have ramifications that you don't expect. So if you have something like, if you have optional dependencies in your graph and you want to pick the most recent version of all the nodes in the graph, what you could do is you could say maximize the sum of all the versions in the graph. And what that inadvertently does is it makes the solver say, oh, well, I can just keep adding dependencies to this graph. So I'll just pick the most recent version of everything, and I'll add as many dependencies to the graph as I can. And so it sort of tends to flip on flags where you didn't expect it to and just build these gigantic DAGs. So we switched all those criteria to minimize, which sort of inherently keeps the graph tight. We assign these weights to versions that use minimization semantics instead of maximization, and that solved that problem. But it was pretty interesting to see sort of the ways that the instructions could go wrong. And then here's another exciting sort of weird case that we found. If you've used Spack recently, you may have seen that if you type this into Spack, if you say Spack install HDF5 with mpitch, you kind of have to help the concretizer along a little bit right now. So you have to say Spack install HDF5 plus MPI to say MPI should be on, and then caret mpitch. And because it's too dumb at the moment to know that MPI has to be on for mpitch to be in the DAG. And so this works. I was happy to see this work. This is one of the problems that people complain about a lot. I can say Spack solve HDF5 caret mpitch, and this is my sort of prototype. and it shows the spec that results, and it's able to resolve it just fine. It figures out that when you ask for mpitch to be in the DAG, that it has to turn on the MPI variant here. And likewise, if it's smart enough to figure out it can turn off variants in different places too. What was interesting was I said, okay, so now I'm going to test it. I'm going to say, build me HDF5 without MPI, but mpitch has to be in the DAG. That should fail, right? And so I did that, and it was like, nope. It discovered that HDF5 can depend on libaec, which can depend on CMake, which can depend on libarchive, which can depend on LZ4, which can depend on valgrind, which optionally depends on MPI for some configurations. And so it stuck an mpitch in the graph way down here to satisfy the caret mpitch that I asked for, even though I said turn off MPI on HDF5. And so, that's not exactly what you would expect. That's not the greatest resolution. The trick here, I think, is that we are exploring through build dependencies here. And so we were able to get rid of this problem by just saying, when you say that a node has to be in a DAG, that doesn't mean that it should be reachable through some build dependency like CMake. Just explore through the link and run dependencies for the thing you're building, and you'll be fine. And so hammering out all the different unexpected behaviors has been interesting. But I think this is a good example of how the solvers are pretty darn smart. The fact that it can find this configuration. I actually went through and said, okay, well, now build with HDF5 without MPI and valgrind without MPI, and it found something else that depended on MPI in the graph. And it was actually somewhat hard to keep MPI out of the build if you did this, until we disabled it for build dependencies. So it's been interesting getting this new resolver working. Getting information about errors is kind of tough. Good error messages is important. You'd like to know why the graph is unsatisfiable. There's a thing called pubgrub for the Dart package manager that generates a proof of why the DAG isn't satisfiable. That's something that we could explore with Z3. The Klingo solver has actually added the ability to have unsatisfiable cores. And so now we have a version of this thing that will tell you what the conflicting constraints are if you get an unsatisfiable graph. And so it will say, the fact that you asked for this version and only these versions are available is why your graph is unsatisfiable. And so things have gotten quite a bit better since I made this slide, but we're still working on error messages for this stuff. All right. So the new concretizer, we should have an experimental prototype of this in 0.16. That's the goal. And then I think we will have a production version of it in 0.17 after we let people try it out a little bit in the wild. But expect to be trying this stuff out pretty soon. It's nearly ready. All right. So finally, I'm going to talk a little bit about the roadmap for 0.16. One of the things that we are trying to do for 0.16 is to make sharing a Spack instance easier. We want it to be possible to have multiple users installing into one Spack instance or installing into their home directory using the same Spack instance. And currently that requires a bit of configuration to get right. We are planning to get rid of some of the configuration in tilde/.spack. The users have been complaining that if you put a compilers.yaml or a packages.yaml or some of our config files in your home directory, it tends to be an unwanted global. If you have two different Spack instances where you're trying to do different things, or if you want to have environments, these configs are still considered. And so I think what we're going to move towards is configuration in environments instead. That sort of conflicts with sharing a Spack instance where we're trying to move state out of the Spack prefix itself. We're going to move, for facility installations into, we're going to make it so that the installations go into your home directory if you're just a normal user using facility Spack. And so reconciling these two constraints has been interesting. I think what we've pretty much decided is we will have configuration associated with different install locations. So in this mode, if you install into your home directory, you'll have some configuration associated with that. And there will be some configuration associated with the facility installs. But we won't have this global configuration that applies to everything across all of your Spack instances. So that's something that we're working out. The other thing that we are working pretty actively on right now is we are going to make compilers into proper dependencies. And the reason that we want to do this is because right now we don't handle a few things well. We don't handle ABI issues between different compilers as well as we'd like. So things like libstandard C++ or libc++ compatibility, we don't model that currently. And so we just sort of leave it up to you if you decide to mix compilers in a Spack graph. It's on you to ensure that they use compatible runtime libraries. The other thing that we don't handle as well as we'd like is things like OpenMP. Same reason, we don't model the runtime libraries, and we also don't handle mixed compilers as well as we'd like to. So every node thinks it's built with one compiler, but that sort of implies that you're building with a particular C compiler, C++ compiler, and Fortran compiler. But for things like Clang, you want to mix compilers, and so people sort of shoehorn G-Fortran into their Clang installation by messing with the configs. And so what we'd like is to have that modeled better in the graph. And so that would enable us to do things like this over here, where if I have package 2 here, it was built with an older version of the Intel compiler that used this version of GCC, and it has this version of libstandard C++. We would put this sort of synthetic node into the graph for libstandard C++. So that if I build another package that then depends on that one, I can ensure that it uses a compatible version of libstandard C++ and that it picks a version of GCC for the libstandard C++ that goes along with what it's building against. So essentially, we would allow you to validate ABI compatibility of your runtime libraries in the DAG. The other thing that we would be doing there is languages would become virtual dependencies. And this is kind of cool because if you look at the Spack packages right now, some of them can get kind of ugly. People have to say that they conflict with certain compilers or that they only work with compilers at a certain version or higher. And what you would rather say is that you need C++ 11 or you need C++ 17 to run your program, or you need Fortran at a particular spec or OpenMP at a particular version. That's pretty much the semantics that we have for virtual dependencies right now, where you can say, I need MPI 2 or higher. We just can't do it for compilers because they're not dependencies. And so once we do this, essentially the compilers will be virtual dependency providers. And the package specification in terms of what language level is needed will be much simpler. You can say, I depend on C++, I depend on Fortran, and we will resolve that with a correct compiler, or we'll check that the compiler that you picked supports what the package wants. So hopefully this will make things a lot better. And with the external find functionality that I talked about earlier, things like compiler detection, where we were doing that sort of as a special one-off for compilers, we can use the external find functionality to implement compiler detection in this model, even though we're switching them from sort of attributes on the nodes to dependencies. All right, so that's it for the roadmap. I guess I can open it up for questions now.
Hey, Todd, thank you. Yes, we have a bunch of questions there. Do you see the Q&A?
Is it in the Google Doc?
It is in the Google Doc, yes. I think it is easier if you just go and take a look.
There are likely a whole lot more questions than we'll ever get time for. So why don't we, Osni, you show your concluding the slide so that people can then leave. But then if you want to stick around, and Todd, if you have time, maybe we could spend another 10 or 15 minutes going through the questions. I don't know if you
can stay on. I can probably stick around for as long as you want to answer questions. I've got an hour. I don't know about you guys.
So why don't you go ahead and start looking at the questions, and Osni, how about you show that last slide?
Okay. Do I have to stop presenting?
No, I'll take over.
Okay.
So yes, thank you for you folks that need to disconnect now. Actually, for the ones that are going to continue with us as well. So I would like you folks to give us feedback so we can improve the series. Some people are asking already about the slides. The slides and the recording are going to be available online, and we'll be also sending the slides. I think I would send again to the people who have signed up.
Yep.
And
there's a new version. I'll send you the latest slides, Osni, so that you can.
Okay, great. Slides. Yes. So. And the next webinar in the series is going to be in about a month, and color mapping strategies for large multivariate data in scientific applications. It will be presented by Francesca Samsel from the Texas Advanced Computing Center, and we so that event is already open for signing up for people interested in that topic. So back to you then, Todd.
Okay, I guess I will share the doc.
Okay, I'll stop sharing here.
Let's see if I can get.
Yeah, that would be great. I think that would help for sure.
I'll share this. Can everybody see this?
Yep.
Okay, cool. And I guess I'll make it
I'll just yes, Todd, just a second here. We are also be sending the questions and answers to folks, and also this will be available online.
Okay, great. I guess for the first question, is there a way to drop into a Python debugger when installing the package? There's not currently a way to drop into a Python debugger because of the way that we route output during the build. And so you do have to use Spack build env. That's on the list of things we could look at, but I think it's probably not on the near-term roadmap. You can basically do debugging of the package on the command line. And we try to spit out exceptions that have information about where things in the Python code went wrong. So yeah, sorry. Okay, so the public Spack mirror where Spack can install from a build cache, which Arch compiler and MPI does it support? Okay, so I should clarify that the current public Spack mirror is just for source code right now. So what we've done is we've taken every tarball of source code and all the patches and resources that you need to build and put them in the mirror. E4S has a public Spack mirror for their builds. And I believe those are targeted at particular containers. And so if you get one of the E4S containers and you get the version of Spack that they built E4S with, you should be able to use the E4S build cache. And so there's more on that at e4s.io. What we are trying to move towards is a model where we essentially have a rolling release of binaries on develop for some combination of architectures and compilers and MPIs. And so I think what we would probably target first would be CentOS, some version of CentOS that we can build in the cloud for x86. Probably some some generation of the Intel chip that maybe does have Skylake and another one, or that does have AVX512 and another that doesn't. And we'd like to support ARM as well. I think for the build caches, and for E4S, E4S builds with mpitch, and so they do that because that's compatible with most of the vendor MPIs on the systems. We don't currently have an open MPI version of it, but typically in a container, if you're going to bind mount the system MPI, you want mpitch. But I'd be interested in hearing what people want because I don't have a good way to gauge that right now. And maybe we can start including more different MPIs. That's definitely the goal, is to have build caches available for the common things that people want to build. All right. So let's see. If I need to pass options down to the CMake that builds my package, how do I do that? So for that, I guess I'll share my whole screen. Let's see. Let's see. Desktop 1. Can you see PowerPoint 2 now? Awesome.
We can see, but yes.
Yeah, okay.
So
yeah, if I go back to the package up here, where I showed cryptkey here, this is how you pass the CMake arguments, at least. So this is a CMake package. That's the thing that gives us CMake support. Essentially, all CMake package does is it automatically invokes the CMake command for you. You could make just a regular package like that, where you write the install method yourself. And in fact, we're overwriting it down here. But the CMake args here, what you can see is like you have to pick, the packager has to decide what CMake args they're going to support. And so the way that you support that is you add some variants to your package like MPI and OpenMP. And then if someone installs cryptkey plus MPI plus OpenMP, then this is going to run with enable OpenMP true and enable MPI true. And so essentially, like the way that we modeled this is you expose the variants on your package. You expose the knobs that you think people in Spack care about. And then you just pass them to CMake in here. That's what happens. But they're customizable. So you could build plus OpenMP minus MPI. You could build plus MPI minus OpenMP and so on. And have 4 different versions of your cryptkey package with different configurations there. And so you can grep around through the packages and see a lot of different ways to pass arguments. All right. Yeah. So could there be a flag to not build the latest version of all dependencies for the particular Spack package? Yes. So for this one right here, I think this answer, Osni, is for the prior question. So for this key question, is there a way to not build the latest version? With the new concretizer, our goal is to prefer the versions that are already installed if they could satisfy the spec. And so we'll keep the current, I guess we could call it deterministic behavior, where it picks the latest version and just goes based on what's in the package. But the default would be that if you've installed an MPI or something, and you try to concretize a new spec, it'll try to reuse whatever it can from what you've got installed, either in your environment or in Spack. So this is something that will happen with the new concretizer. It's not in the current version, but as of 0.16, I'm hoping that you will be able to use this experimentally, and then, you know, for real in 0.17, it'll be the default. So is there a plan to include other build systems? So Bazel is already in there. I want to say Meson is in there too. There are, essentially, Spack doesn't have a constraint on what build system you use on your package. It can do anything. So like the most basic package in Spack is just an install method that does something to get the package installed into a prefix. What we have are these sort of subclasses, like I showed over here. Like this is a CMake package. There's I think a Bazel package and maybe a Meson package in Spack. I'd have to check. But those provide special support for that particular build system. And so that's where this def CMake args is coming from. It's because it's a CMake package. There's a build method somewhere else that's defined around that. That takes this and actually invokes CMake. And there's similar stuff for Bazel. And so like we're using Bazel for TensorFlow in Spack right now. All right. Oh, and it looks like someone already got to this. So that's pretty cool. Does it make sense to have integration between other package managers? So yeah, this is something that we've thought about. Not necessarily for Conan, Hunter, or Nix, but definitely for pip. It's a pain to maintain, like all the Python versions in Spack. And so if for some of these package managers, we could have wrappers around the language specific package manager, I think that would be really good. For stuff like Nix, I mean, Nix is essentially, it's trying to accomplish a similar goal to Spack, but I don't know how we would map a Nix package to a Spack package, because essentially we'd have to parse the functions in the Nix package, figure out the variants and so on. I think the translation would be pretty awkward. So for some of these, no, but for others, yes. Like I think for language specific package managers, it would make a lot of sense for us to just adapt the particular language's package manager and have Spack build with that for a lot of these cases. So I'd say that's on the far out roadmap, but not like near term. How can you tell what options this package supports? Yeah, so this is already answered. Spack info package name will tell you. You can also do Spack edit package name if you want to see the code behind it, but I think Spack info is a better version. The other thing you could do is you could go to spack.readthedocs.io, and there's a whole list of packages over here. And so if you want to see, what options that IDEAS supports, you can click on IDEAS and get, information here about IDEAS, and it links to the package file. It tells you what versions are available, what build dependencies, and so on are there. So there's that. How can I know the process of the build? For example, 6 of 10 dependencies build. Yeah, that's something that we could do better. We print out what we're building right now. We don't tell you what's already installed. Probably the best thing that you could do there is, at least right now, is you could run Spack spec-I. So if you run Spack spec-I thing to build like this, this will tell you the install status of what's, it'll tell you what's already installed. And so you can see what's built and what's not. One of the things on the list that we have to do is, now that we've implemented the new parallel build, we do know up front everything that we're going to need to build. And so we could print a better diagnostic message beforehand saying how far along we are, how many packages are built. But yeah, we don't do that yet. Okay. Is there any desire for or plan to implement CI tests for packages before they emerge in the main repo? So yes, and so that's essentially what we are doing with the E4S pipeline right now. So for the packages that are in the E4S, we are building them. So if the package changed, we will rebuild them, and if it breaks, then we will we'll hold up the PR. And so our goal is to just keep expanding the set of things that we do that for. The obvious problem there is that like one Spack template, you could build that a million different ways. And so what we will likely do is, test some subset of them, or, maybe just the default Spack install HDF5 and hold up the build, or hold up the merge if something goes wrong there. So we'll have some set of sort of canonical configurations that have to pass for a package to build. And right now that's what's in E4S. So you can do this. So can I ask to build a package with the same dependencies another package was previously built with? You can specify them individually right now. So you can say Spack install, say HDF5 caret hash, and then you can say ABC123 here, where this is the hash of existing mpitch, right? And you can actually put the name on that too. You can say mpitch /ABC 1.2 or 123. But you do have to specify them all by hash, so it's a little more tedious than it could be. You may want to use Spack YAML for those types of preferences. Oh, yeah, so some other people have some recommendations, so that's cool. This is actually good advice. If you put packages preferences in your Spack.yaml, so go to the build customization section of the Spack docs over here, and you can go to concretization preferences. You can sort of pin what your environment is going to do. You can say always build with this mpitch or always build with this version of a dependency, and you can construct an environment where everything is built with just that. So that's a way to do it. All right. Will Spack external find packages installed by Spack already by a prior Spack install command? So right now it searches your path. It does not search what's installed by Spack. So no, but those things could already be used as dependencies because they're installed. So there's that. And I think this is related to the earlier question of, will you reuse existing installs more aggressively? And the answer to that is yes. All right. Is there a way to keep the source code of a package? Yeah, you can do this. So this is one way to do it. Spack install -- keep stage will keep the build around, but then that's still in temp. So I would say this is still in temp. So it's a little volatile. What you can do is, let me see if I can find it over here. If I bring up, I'm blanking on what the argument is. And my shell session is slow. You can say Spack install -- source, and it'll keep it around. So let's go back here. Yeah, oh, okay, thanks. So Spack install -- source, we'll put that into share Spack source. Is there any automated testing of E4S with CUDA? Not yet, but there definitely will be. There's an ECP funded project to test E4S with all 3 different GPUs that DOE cares about. So E4S is going to get tested with CUDA, AMD GPUs, and the Intel GPUs.
We are going to have a webinar on E4S in, I think, January.
Yeah, so definitely listen to that. E4S will be tested in a lot of different environments, and you'll see that expand. There is a ECP contingency project for next year where basically we're going to be working with the E4S team to ensure that we're running it and building it regularly on the different exascale machines, or at least the early access machines at the different facilities. Okay, what are the differences between Spack and Geeks? So Spack and Geeks, so Geeks is a lot like Nix. Geeks is basically Nix but implemented in Scheme. And it's also the GNU version of Nix. It has a more, I guess, restrictive license. I would say the main difference between Spack and Nix or Geeks is that Spack packages are templated, and that, you know, if you want to build lots of versions of something in Nix or Geeks, you end up having to hack package recipes a lot more. So the packagers write, you know, one version of something, and yes, you can have, you know, you can swap different function parameters in and out of that, but I would say it's generally more cumbersome to do something like swap a compiler into a Nix build or build a Nix build with a different parameter. And so, like, what I would say is that, you know, if you're building with Nix and Geeks, you're hacking, you know, either Haskell-ish Nix language or Scheme, and if you're building with Spack, you're writing templates in Python. And that's sort of a fundamental difference. Spack is designed to build combinatorial versions of things, and Nix and Geeks are very much focused on reproducible versions of exactly this thing. There's a good reference on that on Nix discourse, and so, you know, so if you go to discourse, yeah, this one, discourse.nixos.org, and you search for Spack on here. There's this unanswered question, but there's this question on using any package version in Nix. And so you could read this question. You can paste this into the chat. So see that if you want sort of the core of the difference. Yeah, all right. How does Spack, stacks, and concretize together interact to force consistency of the packages being installed? Okay, so this is complicated. Concretize together is really not for stacks, it's for regular environments. And so concretize together says, make this virtual environment a lot like, you know, a single prefix environment in a regular OS. Make sure that everything is concretized together. So you can actually enable that on environments now. And that might be a good answer to one of the prior questions where somebody asked, how do I make sure that my builds all have the same dependencies? Well, if you do concretize together, they will. And it'll fail in certain cases. If you're doing a Spack stack, you're probably not concretizing together because you want to build an environment that has things built with different MPIs and different compilers and so on. And so right now, what we do is we expand the matrix to just the product of the roots. And so you'll get specs like HDF5 built with this compiler and this MPI, HDF5 built with this compiler and this MPI, and we concretize them separately. And so that means that there will be some duplication in the dependencies if there are small differences. With the new concretizer, we will be able to minimize that. And so essentially we'll be able to say, build me the configuration where the roots are different in these ways, but the other dependencies are minimal in that they're shared as much as possible between the different roots. And so that's something that I think will be really good for facilities, is that we'll be able to optimize that, you know, for real, and build sort of the smallest stack for a given specification that we can. So hopefully that answers that question. Let's see. What's the reasoning behind defaulting to using Spack's own source mirror for source code instead of using it as a fallback? Our mirror is more reliable than most of those other sites, and it's out of S3. So, I mean, one of the reasons that I like this is because we've been talking with AWS, and we're looking at maybe putting our mirror into CloudFront. So we would actually have a CDN on our mirror. And also, I guess, one of the reasons that we did this is it's among distributions, it's considered kind of, you know, a good faith thing to do to provide a mirror of your own so that you're not spending someone else's bandwidth on your project, which is essentially what we've been doing so far. So now we're providing the downloads. The Spack traffic goes to our site and we pay for it. So I guess that's the main reason. I'd be curious to hear why we shouldn't do that. All right. Are all heuristics used in the Spack case for the new concretizer deterministic? With optimization, yes. So if you don't use optimization in the solve, you will just find any solution that works. And so you could potentially find like an old version somewhere that still satisfies the spec, but maybe is not deterministic. When you add optimization to that and you say, always find me the most recent version, find me my most preferred compiler and my most preferred virtual implementation, it is deterministic. And so that should not be a problem with the new concretizer. All right. I think this was originally the first question, so this is kind of exciting. We must be getting near the end.
Right.
All right. So what's the question here? Can we create an environment? So I think we answered this in the presentation. So yeah, Spack installs things with RPaths, but you can also make these environments to run your software. So essentially you could think of Spack environments as like virtual env, but for anything. So yeah, you can have a Fortran virtual environment in Spack and run your climate code in it. That's totally possible. And that was the intent with the Spack environments, was to kind of unify this idea of manifests and lock files from systems like Cargo or from Bundler with the notion of an environment, where essentially like now an environment is this spec.yaml file plus spec.lock plus the ability to get it all into one environment in your shell. And then, yeah, so I think, so I don't, I guess if you have a code where you have to recompile to change a parameter, you're still going to have to recompile to change a parameter. We can't change that without patching the code. So there's that. So, but you can make two environments for that. You can make one environment with the code built one way and another environment with the code built another way. And they would share underlying implementations and just have separate versions of the root code. So you could potentially use Spack to do that in an efficient way without wasting a lot of disk space. Okay, and then I think some other people have tried to answer that. All right, considering the example given for language features as dependencies, since compilers claim to be C++ 17 compliant when they still aren't, do you consider managing specific toolchain differences about language support? So yeah, I think we could do that. In Spack, packages can provide more than just one virtual dependency. So I mean, you could have a C++ implementation or a C++ compiler that provides like lambdas at one version and other C++ features at other versions plus lambdas, and then you could have a more fine-grained specification of what virtuals you need instead of just doing the language level like this. I think we could also have both. I mean, you could have the compiler provide C++ 17 if it's fully compliant, and then we could have others, the finer grained things for older versions of the compiler that maybe only support a subset of features. And then it's kind of up to the packager to decide whether they want to fully enumerate that or not, and that would determine which compilers they could build with in Spack. Okay, so what learning path will you recommend to be able to create new packages that are not already in Spack? So what I would say is so first of all, check out the first slide of the presentation because there's a tutorial in 2 weeks that you can take, and it's 2 days, so you can learn all that you ever wanted to know about Spack and contribute that way. The other thing that I would do is just try making a package. You can look at the tutorial online. We have links to it. There's a whole packaging guide, so definitely look at the packaging guide. It is down here on the docs, and it's quite long. Like there's a lot of information in here, so you could read this. And then I would say that probably the best way to get feedback on your package is, even if it's not working, just submit your package as a pull request to Spack, because I don't know, I like to say that the best way to get the right answer is to put the wrong answer on the internet. People will comment on your package and will give you feedback. And if that doesn't work, then there is Spack Slack. So you can go to github/stack/Spack over here. And if you click this button right here, this Slack button, it will take you to this page over here, and you can get an invite to our Slack channel. There's 648 people registered on our Slack channel, and maybe 50 or 60 are online at any given time. And so if you just ask a question there, people will be happy to help you make a Spack package. So, and that's over here in, well, I don't have it open, but you can try out Spack Slack. It's available. Let's see.
Get into the end, yeah.
And then I think, okay, well, how should packages be handled where dependencies change frequently? Yeah, so I think at the moment these things just get messy, and we don't have a very good solution for packages that transition to a different build system. We've started moving some of them to like sort of older legacy packages with the old build system. This is something we probably ought to address once the new concretizer is in and we have a little more bandwidth to deal with stuff like this. I think these are two really good questions that we don't have good answers to. Are there if you want examples of these things where the dependencies change, look at like some of the compiler packages. So look at LLVM, look at GCC. They have dependencies that change pretty rapidly. And they just write code in the package. So like one of the nice things about Python is that right inside your class definition, you can put loops and things. And so, LLVM has a loop over all of the different configurations of it that are valid. And so you don't have to write everything out explicitly. You can actually just have the package implicitly enumerate all the different ways that it can be built. That can be harder to read, but that's how people do it now. So I'd say look at LLVM and GCC, look at some of the more complicated packages in Spack, and definitely if you have suggestions for how we can improve that, then I mean that would be awesome. Are there plans to support multiple download URLs depending on variants and spec features? Oh yes, we would. I would like to have. Okay. So for Spack binaries, we can do this. So if you make a binary package like E4S does, Spack already handles installing different binaries for different configurations that way, because you don't have to specify that in the package. But for things that can only be installed from binary, we currently don't have a when clause on the version directive. And so we can't say when I'm at this version, download this tarball, when I'm at this version, when I'm on this architecture, download this tarball, when I'm on this architecture, download this tarball. We don't have very good support for that. I would expect that to be added in the next couple versions of Spack because it's a really common question. We just haven't had the bandwidth for it given the other features that we're working on. Is there already a Linux distribution that uses Spack as their main package manager? No, not yet, but maybe once we have glibc in there, they will consider doing that. But I don't know. We could make one. We could call it Spack OS. I don't know. It would be a really cool thing to do once we have compilers as dependencies and these runtime libraries modeled in Spack, to think about that, because I think you could basically make, I don't know, distroless containers with Spack, where we don't rely on a base image at all. We just build from glibc up and build your application that way and give you a container. I don't think that would ever be our default mode, or at least not in the near future, because if anyone on the call has ever tried installing Gentoo, I think it would be kind of like that if you had to build everything from the kernel up to get your app built. So we don't want that. But you know, there's definitely interesting things to think about in that space. So yeah, I guess stay tuned. That's longer term, but it's interesting. And I think I did all the questions.
Yeah,
so
that's great, Todd. Thank you. I'll just ask you, to take another pass later to see if everything has been covered in this Q&A.
All right.
Yeah, thank you. Thank you for everybody for sticking with us for another 30 minutes here almost. Yeah, great. Thank you. Thank you all.
Yeah, thank you, Todd, very much. Thanks, everyone. We should have the video out in about a week in case you have colleagues who missed it. Todd, thanks for sticking around. Osni, thanks for putting together another good webinar, and everyone have a great rest of the week. Thank you.
All right.